Multiprotocol label switching, MPLS, is a routing method utilized in telecommunications networks, guiding data flow between nodes through labels rather than network addresses. The primary function of MPLS is to pinpoint established paths between endpoints, rather than just identifying the endpoints themselves. This technique allows for the encapsulation of various network protocol packets, accommodating a wide range of access technologies such as T1 or E1, ATM, frame relay, and DSL. Initially developed to streamline packet forwarding by decreasing the dependence on intricate routing table searches, MPLS now primarily focuses on traffic engineering, differentiated services quality of service, and BGP, MPLS IP, virtual private networks, VPNs, due to the advent of hardware-based forwarding engines that have enhanced forwarding speed. In an MPLS network, decisions regarding packet forwarding are made based solely on label content, obviating the need to inspect the packet itself, thus facilitating the establishment of end-to-end connections across varying transport mediums using any protocol. MPLS bridges the gap between traditional OSI Layer 2, data link layer, and Layer 3, network layer, by operating at a layer often regarded as 2.5. This unique positioning aims to offer a unified data transport service for both circuit-based clients and packet-switching clients that adopt a datagram service model. Notably, MPLS is versatile enough to carry a wide array of traffic types, including IP packets, as well as native asynchronous transfer mode, ATM, frame relay, synchronous optical networking, SONET, or Ethernet traffic. MPLS can operate in both IPv4 and IPv6 environments, leveraging suitable routing protocols to function effectively. Originally, the core objective behind MPLS development was to enhance routing speed, which has become less of a concern with advanced switching methods like ASIC, TCAM, and CAM-based switching that can efficiently forward plain IPv4 at speeds comparable to MPLS-labeled packets. Today, MPLS primarily excels in limited traffic engineering and the provision of Layer 3 or Layer 2 service provider type VPNs over IPv4 networks. Standardized by the IETF and RFC 3031, MPLS finds application across a broad spectrum, from connecting a mere 2 facilities to extensive network deployments. In practice, MPLS is predominantly employed for forwarding IP protocol data units and virtual private LAN service, VPLS Ethernet traffic, demonstrating its significance in telecommunications traffic engineering and MPLS VPN services. Operating in conjunction with the Internet Protocol, IP, and its associated routing protocols, MPLS facilitates the creation of dynamic, transparent virtual networks capable of supporting diverse service models and enabling effective traffic management. A label switch router, LSR, also known as a transit router, is a critical component in an MPLS network responsible for routing packets based on labels. These routers receive packets, utilize the label within the packet header to determine the next hop on the label-switched path, LSP, and replace the label before forwarding the packet. On the other hand, a label edge router, LER, operates at the edge of the MPLS network, adding and removing labels on packets entering and exiting the network. In the context of an MPLS-based VPN, LERs serving as ingress or egress routers are commonly referred to as provider edge, PE routers, while those functioning solely as transit routers are known as provider P routers. The Label Distribution Protocol, LDP, or Resource Reservation Protocol, RSVP, is utilized to distribute labels between LERs and LSRs, enabling the exchange of label and reachability information to facilitate packet forwarding. Label-switched paths, LSPs, are established within the network for various purposes like creating IP virtual private networks or directing traffic on specific routes. When an unlabeled packet enters the ingress router, labels are inserted into the MPLS header based on the forwarding equivalence class, FEC, of the packet, and it is forwarded to the next hop router. Upon receiving a labeled packet, an MPLS router performs swap, push, or pop operations on the packet's label stack, allowing for efficient packet processing and forwarding based on label contents. MPLS headers facilitate protocol-independent packet forwarding, eliminating the need for protocol-dependent routing tables and costly IP longest prefix matches at each hop. In the MPLS network, the egress router is responsible for popping the last label from the packet, leaving only the payload to be forwarded based on routing information. Penultimate hop popping, PHP, is a technique employed to offload the egress router by having transit routers pop the last label before reaching the egress router. MPLS enables various services like end-to-end quality of service, QoS management, with specific label values reserved for different functions like implicit null for IPv4 and IPv6. Label-switched paths, LSPs, are set up across the MPLS network based on specific criteria, with LERs, transit routers, and egress routers playing distinct roles in path establishment and packet forwarding. Paths can be managed using standardized protocols like Label Distribution Protocol, LDP, and RSVP-TE, providing flexible and efficient routing mechanisms within the MPLS infrastructure. MPLS works alongside Internet Protocol, IP, supporting dynamic virtual networks, traffic engineering, and Layer 3 VPNs with overlapping address spaces, enhancing network manageability and performance for service providers and users alike.